All right? In fact, after we do Towers of Hanoi. So I would say anybody who understands recursion should understand Towers of Hanoi. It's just one of the classic examples.
Can you go back to the last
I
slide?
don't really want to. Why?
Where does 3 come from? The plus 3?
Because it's the A, B, and C. No problem. I felt we were done with that page. We're going to do more of these.
Don't focus on the.
Yeah, we're going to do more recurrence relations later. All right? Let's do Towers of Hanoi. And I do think it's a classic problem. I grew up in a math household, and there were always puzzles on the table, and one of them was always Towers of Hanoi. And, how many people saw Towers of Hanoi before you were 10?
Is there an app?
Maybe.
Probably is.
Maybe, probably is an app. Anyway, this is the one where on last test I stuck it in as a bonus question for everybody to get for free, and people still couldn't get it. All right? So here's the problem. Does anybody not know Towers of Hanoi now in your life? You got 3 towers, right? And you got pegs of different. You got 3 pegs, and you got discs of different sizes. And there's 2, and you want to get them from here to here. And you have 2 rules. The one rule is you never can put a bigger disc on top of a smaller disc, and the other rule is you can never pick up more than 1 disc. Those are the rules, right? So you want to see, how do I get them from here to here, right? You can put the small disc here, and then the next disc, well, you can't put it here on top of the small disc, so you have to put it over here, right? And now this disc, the 3rd disc, you can't put it anywhere, right? So you have to take the small disc and put it over here, so you can move the 3rd disc over, right? That's how you start. And so now we want to say, how do you solve the whole thing, right? And, you can say, oh, the job feels very daunting. The whole computation, right, is confusing, right? And so you just be lazy, and you get friends to do it for you, right? So I'm claiming not only is this an algorithm, but it's pretty much the unique algorithm. All right? There's only one way to do. You can always move things back and forth, right? But efficiently, this is the way to do it. At some point, you have to move the big disk from here to here, right? At some point, you have to do it. And when you're moving the big disk from here to here, everything else has to be in the middle, right? Everybody agree with that? Yeah. So now we have 2 subproblems. Subproblem is, how do we go from here to here, and how do we get from here to here, right? And how do we get those problems solved? You gave it to a friend, right? Because it looks like a smaller instance of the same problem, right? So here, how do we get these smaller disks to move? We get our friend to do it, right? Here are things coming in the opposite directions. I always love that, right? This friend, I get my friend to move it, and another friend to move that. Everybody kind of follow that? And so what's the algorithm? That's the entire algorithm, right? What we do is I get my friend to move the n-1 disks from here to here. And then we're in this situation, and then I personally move this disk from here to here. And then I get another friend to move the disks from here to here. That's the algorithm, right?
Can you explain how the plans actually go?
No. No, absolutely not.
Don't want to get stuck.
We don't want to micromanage our friend, right? It's a smaller instance of the same problem, so we don't have to worry about our friend, right? All right, so that was me doing the guy in the middle. All right, so here's here's the code. And to make it a little bit easier, we're going to have three inputs. We're going to have the name, right? We're saying that you're moving the disks from some tower to some tower, and the towers are named 1, 2, 3. So source is the name of the tower that we're coming from. Destination is the name of the tower we're going to. And spare is the third one, right? And why did I put the spare? Well, if you know this and this, you can calculate that. But why bother? I'm going to just tell you it will make the code easier. All right? And so what do? Well, if you have no disks to move, then you do nothing. Right? Otherwise, I assume I have at least one disk to move. And what do? I recurse. I'm trying to move n disks, right? And let's say what our precondition is already, right? We have various poles, and you look at the first n disks, right? They're on the source pole, and then the other disks. These are disks n plus 1 to n. Where are they? They're somewhere down here, but we don't care. Right? Everybody buy that? It's kind of what it's saying. The smallest disks are on this source. The larger disks are somewhere. Right? And what is our goal? Is to move these disks from here to here. Right? How do we do it? Well, we get our friend to move n minus 1 disks from the source to the spare, right? Now, we have to make sure that it's smaller and meets the precondition, right? It's smaller because I have to move n disks, and he has to move n minus 1 disks. That's why it's smaller. Why does it meet the precondition? Well, if we have this picture where n plus 1, all the bigger disks we don't care where they are, then we just move that line up. These disks are here, and we don't care about the bigger disks. Right? Does that make sense? So the precondition is made, and so what does their friend do? Our friend moves them. Right? The n minus 1 disks get put on the middle pole. Right? And then I say, and what are we asking him to do? We're asking him to move him from the source to the spare. Right? And he has the destination is his third guy. Right? And then I personally move the nth disk from the source to the destination. And then I get my other friend to move n minus 1 disks from the spare to the destination.
So we're moving it to the source to the spare.
Yeah. It's the third pole.
Yeah. But here we're moving it from the first line. You're moving it from the source to the spare, right?
Yes.
So I get what's happening there.
Yeah.
Why do we need to have destinations there?
Because the friend, it's useful for the friend to know which the spare is. Okay. Right? This is my friend's source. This is my friend's destination.
Yeah.
This is my friend's spare.
Okay.
Right? I could replace this with calculate who's not there. Right? In fact, I could say, here I could go 1 plus 2 plus 3 equals 6. So the third guy, Z, is going to equal 6 minus X minus Y. You could do something weird like that to calculate who your third is. But it's just easier I'm going to tell you who the third one is, right? I'm telling you the role of the 3 poles, right? The first one I list is the source. The second one I list is the spare. There's the destination. The third one I list is the spare, right? So then the first guy is going from the source, where they are, to the spare, right? And why do we do that? It's because I want to move it from the source to the destination, right? And then we can get a friend to move them from the spare to the destination.
And that one in the middle. Okay, gotcha.
Right? Everybody kind of got that? All right, so one way you can think about it is that there's a company, a Tower of Hanoi company, right? And you could imagine that you start off n equals 0 where you do nothing. That's the job I want, right? Or you could get the n equals 1 job where you learn how to move one disk, right? And then you get promoted to the n equals 2 guy. And when you're trying to move 2 disks, you get the guy, now you have 2 people below you, right? You have 2 n equals 1 people below you. And you get them to move the first disk, and you move the second disk, right? And then you get promoted to n equals 3, and then you have 2 n equals 2 below you who have 2 n equals 1 below them, right? And you learn how you're going to do these things. You promote it. Or you can just live big and say, right, I'm just going to pretend I'm the president, and I have to move n disks, and the way I do it is I get my vice presidents to move n minus 1, right? So that's our code. What's our running time, right? So here we're going to do it a little bit more work than we did the last one, right? See, this is our recurrence relation. If you have 1 disk, then you have to move it. If you have n disks, then you have 2 friends with each of size n minus 1, right? And I move 1 disk myself, all right? So the plus 1 makes the math a little harder, so let's ignore it, right? Now actually what we're asking is how many times does the little disk move, right? Because if there's only 1 disk, then it's the little one and it moves. And if you have a lot of disks, then the number of times the little disk moves is 2 times the number of times it moves when you have 1 less, right? So anyway, now we got that, and then kind of what we were doing over here, you can unwind it, right? And then you unwind it again, and you keep going, and you see it's 2 to the n.
Yeah, okay.
Right?
We learned it before.
Everybody buy that? All right. So actually, yeah. So if you solve it with a plus 1 in there, then it's 2 to the n plus 1 or 2 to the n minus 1. There's a minus 1 there. Anyway, that's the whole algorithm. And any questions about it?
Yeah. Well, I'll answer the question. So I think like the takeaway from this is like you can have like a complicated problem, but because we're thinking about the algorithm and we're not worrying about how to actually like implement, like go from here to here with code, we can make it like it's a lot easier to actually do it.
Yeah.
Okay.
So what are we saying on this slide? Right. So here we're going to prove by induction, right, that it's that. Right. The first guy has to move n minus 1 disks, so that's how much time the first guy takes, right? And then the guy in the middle does 1, and the guy in the second guy does that many. And then if you do the math, this plus this equals this. Right? Proof by induction. Everybody good? Yeah. I do come up with what I think are fun problems sometimes, but then you guys die on the tests. I don't know why. Right? This was such a great problem I had on the test. Start with the pieces distributed anywhere, but they're stacked from littlest to the biggest, and then you have to figure out how to finish it from there. And it was just about as hard as the original, but it didn't go over well. All right, so here now let's do this. Solving this recurrence relations again, all right? I think I've said a few times that if you have a number, you better not subtract 1 from it, right? So here we're subtracting. Our friends are getting an input of size n minus b, and I have a friends, right? And I do some work myself, right? So we're going to say, what's the size of the instances? Well, they're going down by b, right? So it comes down by b each time. So what's the height of the tree? Right? Now we can actually get down to a height of 0. So we solve, and we get the height as b over h. Right? Doesn't that make sense? If you keep subtracting b, you have to do it b over h times. And that's why I had here, when we were subtracting 2, that the height was h over 2. When you subtract 1, then the height is n versus n over 2. Everybody got that? That's the height of the tree. And then, how much work is done at each level? Well, the f of that. And then how many stack frames? Now, the stack frames is still growing exponentially. Right? I have 2 friends, and they have 2 friends. Right? So we get this recurrence relation, and then we get this work at each level. Everybody buying this? Right? And I don't care about the rest of this. Right? Dude, that's exponential. Right? It's a to the raised to the power of the height. And the height is order n. It's exponential. Right? Everybody see that? Don't do this. All right? Now, there's 2 ways of fixing it. One way you fix it, you divide it here. But if you have to have that, there is a way in which it's okay to do n minus 1 size. When can you do it? Friends? I heard something about friends. More friends? No, not more friends. Less friends. How many friends do we want for it to be okay? 1 friend or 0 friends, right? Right? So if we have 1 friend, then everything is the same except the number of stack frames at every level is 1, right? And so now we don't have that exponential growth here, and we just have to sum this up. And that's the sum. I mean, for example, suppose I want to do insertion sort, right? I can have my friends sort n minus 1, right? My friend sorts n minus 1, and then I insert the last, right? That kind of thing. Alrighty. So that's just saying, if a is bigger than 1, just don't do it. And if a is 1, then it's an arithmetic sum or a geometric sum. Yep.
Why did you say it was earlier to add back subtract by 1?
Well, because if you subtract by 1 or by, it's about to subtract.
Yeah, it's not to subtract.
Doesn't matter if it's 1 or b.
It's going to be size.
Yeah. Yep. This table we're dividing by b, and here we're subtracting by b. Right? Big difference. Yeah, for sure. This is the one we were doing before, and this is the one we're doing now.